Is this video?
Yeah.
I didn't hear anything from the video. Is there any sound in the video?
Yeah.
I didn't hear it.
Okay. You're not able to hear it?
No.
Okay. Okay. Then what I will do, I will save this and then I will remove all those video voice. Then I will explain. That's better, right?
Or you can send me the file itself, so
Yeah.
I can
Yeah.
play it. Yeah.
Yeah. Okay. No issue. I will send you. That is separate one. Yeah. So mainly here, what I was trying to explain here, the strength of tubular joints means where we have all our offshore CAN members. You know, right? CAN members, Randall,
Yeah.
brace members and CAN. This CAN member, how we are designing it. That's the main topic for this presentation. This, if you see this guideline, that is giving only the static design of joints. What we are going to see, that is a static design of joints. But there are some more also. It is there. Fitting design also it is there. So that will be the next chapters. It will be there in the APRP2A. So it's mainly from APRP2A. That's the one it's giving guidelines for us. Okay. And suppose if we are not following these guidelines, instead of these guidelines, we can have some alternative methods also, reasonable alternative methods, provided that gives the reliable estimate, like some numerical methods like FEM analysis or some other analytic techniques can be used. But we need to demonstrate that strength of joints is reliably estimated. We should not underestimate or overestimate. Such analytical numerical techniques calibrated and benchmarked to suitable test data. That means like all these FEA analysis, finite element analysis, all they need to have some experimental test data. In actually, what they do in the APA database, they have some joints and all. They physically fabricate, and then they will apply load, and then they will come up with how much is the allowable load, and then they will formulate some empirical equations. Then they come up with this formulation for calculating the strength. Like that, we need to calibrate and benchmark if you are using some other techniques. Okay, that's what they're telling. And these recommendations presented in this APRP2A, that is based on the characteristic strength of the tubular joints. That means like all are lower bound. Lower bound means like conservative estimate. So always you remember that characteristic strength that corresponds to lower bound estimate. Suppose if the joint we are saying that it is failing at say allowable load of sub 10 ton, it means that that's lower estimate, but usually it may go even beyond that. Instead of 10 ton, it may go to even 12 tons also. It can be able to take. Okay. So one more thing, care should be taken using results of very limited test programs. Yeah, this is what they're telling. Like in APA or P2A, the test database, they have limited test only they have done. So we need to consider some lower bound value only. We should not have some higher bound value. That's why they are giving this kind of careful statements like we need to consider lower bound estimate, and that's why we need to consider some reduction factor, because they have some limited number of tests, and each test if it comes like a 10 10 20 10 30 10 like the different capacity, it doesn't mean that it will be we can take as it is. We need to apply some reduction factor because they have very small amount of data only. They don't have a very large number of data to give this formulation. So we need to consider some reduction factor. We need to impose some reduction factor on the calculation of joint strength. That's what they're trying to tell. And one more thing, these materials, if you see, and these guidelines, they are giving some specific material related yield value and all. If you see the yield value of the card, this the card member is the right. This is the card member. This is the brace. So in the card member yield value, in the calculation of joint capacity, we need to limit to 0.8 times the tensile strength. You know yield value and tensile strength. If you see the stress strain diagram, it will come something like this, right? Upper
Yeah.
yield, lower yield, and then ultimate tensile. This is the tensile strength. Here it you will have some yield value, lower yield and upper yield like that. So this tensile strength, whatever it comes, we need to limit to 0.8 times. That should be the yield value. Okay, that's what they're telling. Whichever is minimum yield value or 0.8 times tensile, whichever is lower value, that should be we need to consider in the calculation of the joint capacity. Okay, and the joints involve often close proximity of welds. It means like you see the brace here, one weld will come, here one weld will come, one more brace also, if it comes, one more weld also it will come. So joint involves close proximity of welds. If you see one weld to another weld, some we have only 50 mm only gap. So this has a close proximity of weld and from several brace connections, right? So high restraint of joints, this kind of so many close proximity of weld, it will have large strain concentrations. If large strain concentration happens, there is a potential for cracking and lamellar tearing. That means if you have the card member like this is the card member. Imagine this is the thickness of the card. So we have the brace like this. When some tensile load is coming, it should not tear like this. That's a lamellar tearing through the thickness direction. This is the thickness of the tubular card member. This is the brace member. It should not tear like this. So because of this large strain concentrations, there is a possibility for this cracking or lamellar tearing. To avoid that one, only adequate true thickness toughness of the card steel should be considered as an explicit requirement. It means whenever we are ordering material, we need to tell that at this can member, this material should have the true thickness toughness requirement. They will call TTT, true thickness toughness requirement. Then only it will not break through crack or lamellar tearing. That's what it means, these sentences. You understand, right?
Okay. So is there any geometry that or the range for this thickness?
No, whatever may be the thickness, we need to consider always true thickness property for the joint location.
Yeah, how can make adequate through the thickness?
Yeah, this is called a chemical compound. Like when they are manufacturing the material, that time itself they will ensure that the chemical composition they will fix such a way that it will have true thickness property. When they take sample and do the testing, it will have ductile property. If you see this Z35, Z30 like that, they will make some testing requirement. Z35 means like if you apply the load, it will elongate, right? It will elongate like this. So cross-sectional area will reduce. So this reduced cross-sectional area and original cross-sectional area, if you compare 35%, it should go this much thinning. That means if it is going this kind of thinning, it seems it is having sufficient ductility. So they will ensure that this by adjusting the chemical composition, this kind of toughness is achieved. Okay, so we need to define when we buy the material, this material should have TTT properties. That means then automatically the producer, whoever is producing the material for this kind of can members, they know that chemical composition has to be adjusted so that they could achieve this ductility property of the material. It should not break you like a brittle. It should have some ductility. And that ductility also it should have Z35. Z35 means 35% at least it should come down the cross-sectional area. That much it has to thin. That means like it will be having very very like a thread kind of thing, right?
They call it as a neck, right?
Yeah, neck. And also it's called like very ductile. If it is brittle, it will not have this kind of malleability. Okay.
Okay.
Yeah. The next thing is next sentence. If you see existing platforms that are either being reused or reassessed could have uncertain material properties. That's possible because If it is installed very long back, then we don't have the proper documentation for the material properties, whatever used for this kind of existing platforms, then that probability can happen. So in these instances, we need to what they have to do. They have to do the material test on the samples removed from the actual structure. So in the actual structure, they have to take some samples, then do the testing, then they can get the properties. That properties they have to use it. This is how the APRP2A and all it recommends. Okay. Then if true thickness properties, true thickness toughness of a joint is ill-defined, if it is not properly defined, suppose if they miss to define it, then inspection for possible cracks or lamellar tearing should be considered. That means that if it is true thickness properties is not there, then there is high chance that it can have the potential for lamellar tearing or crack initiation. So they have to plan the inspection accordingly. So they have to carefully
So
do the inspection of the joint.
it
Frequency
must
of
be
inspection
to
should be
be
more.
TTT, or I have
No,
a choice. If it's not
no.
there, I have to make the inspection, or it should
There's
be
no
like T.
there's no choice. Like we need to have all these true thickness property when we are doing the
Okay.
new structures and all. If suppose if it is a old structure, then they have to increase the frequency of inspection. They have to see frequently. They have to go and see whether these joints crack is there or not there, whether the fitness of the joint is okay or not okay. Like that, they have to see it. Okay.
Okay.
Yeah. Then let's see. I just want to show here this joint configuration. See here, this is the brace member and this is the card member. Capital D is related to card, small d is related to brace.
Yes.
And you see this is the crown toe, this is the crown heel. So whenever the brace is coming like this, it should be the toe, it's the heel, and this point is the saddle. Okay, this terminology we need to remember. This is the crown toe, this is the crown heel, this is the saddle point. These points they used to tell, because the way we need to know this one, you will come to know like when we are doing some long seam means like all these tubulars, the tubulars are there, right? How they are manufacturing tubular, they will take the plate and then they will roll the plate like this and then they will weld it. So this weld will called a seam. This that means like here in this location weld you can see. Okay.
Okay.
So this weld seam, how we have to place with respect to crown heel, toe, crown heel, those kind of requirements are there. That's why we should know like what is crown, toe, crown heel, all these things. Okay.
Okay.
Yeah. And here, if you see, there are three geometrical parameters. These three geometrical parameters are very important parameters. One is beta. Beta is nothing but diameter of brace to diameter of card. This usually we call the diameter ratio. And tau, you see, tau is thickness of brace to thickness of card. This is thickness ratio. So the diameter ratio and thickness ratio, and one more is d by 2t. This is the card parameter. Card parameter means gamma parameter. This diameter of card, thickness of card. So here they have the limitation also. The gamma should be within this 10 to 50. It means, for example, if it is minimum is 10, gamma is minimum 10 means d by t, how much it will come? It will become 20, right? 2 into 10, 20 it will come. So gamma is 50 means it will become 100. Maximum is 100 d by t, right? But 100 it is with respect to this geometric parameter validity range only. But last time we have seen if the d by t goes more than 60, then we need to consider some local buckling and all. Do you remember that, right?
Yeah.
So but this joint parameter, it will be within this range. Suppose if this is going beyond this range, there are some other methods like some approaches we need to do it, that we will study it later. And one more thing, you see that theta is the brace angle, 30 degree to 90 degree. That means this is our card and this is our brace, right? So this theta, should be minimum 30 degree or maximum it can go to 90
90.
degree. Yeah, that's the max. And yield value should be less than or equal to 500 MPa. And other one is for K joints, this gap is there, right? This gap and
Yeah.
diameter. Based on these two also we have some limitation. That limitation, 1 minute, we will show it there here. See, G by D, there is a limitation. Here you see, right? G by D,
Yeah.
less than or equal to 0.6. So that means minus 0.6 less than symbol G by D. Suppose if I take the D this side, gap should be more than 0.6 times diameter. Minus 0.6 times diameter, like that comes. That means this gap.
How
Okay,
can G be n minus?
Yeah,
If
G
there
cannot
is,
be in minus. If it is minus, if G is minus means what will happen? It will be overlapping joint. It will
yeah.
come. So
Minus
overlapping
minus, it will be
joint.
overlap.
Yeah. So we normally avoid, tend not to choose the overlapping joints, but in some cases it is allowed also. If it is overlapping, then we have some certain requirements that also we
Okay.
can see it in the coming time. Okay.
Yeah,
Coming
yeah,
slides.
okay.
Yeah. Then next, if you see the basic capacity. So this basic capacity is the equation, this allowable capacity for the brace axial load, and this is allowable capacity for the brace bending moment. That means what? Like suppose if we have the can like this and brace like this, okay, some load it will come. So what's the maximum load we can apply here? That's the allowable brace axial capacity. That is defined by this parameter, this formulation. So we have to find out. So if it is after finding this value PA, this PA value we know, for example, say 10. After coming to know, substituting all these parameters, we are coming 10. So actual load should not go more than that, otherwise it will get punched, right? This brace will go inside the card. So to avoid that one only, we need to first calculate what is the capacity of this brace axial load for punching, to avoid the punching of the card. And the same way the moment also, MA is nothing but allowable capacity of the brace bending moment. This brace allowable capacity of brace bending moment. Suppose if moment is too high, then it will come like this. One location it will punch inside, it will come up. So you can see this card might have oversized. So to avoid all these things, there is a limitation. We cannot go more than this MA value for this brace, and we cannot go more than this PA value for the brace. So it depends on how to calculate this PA. That's what it's defined here in the APA RP2A. We will see here. So it depends on some parameters like a QU, QF, and then FYC. FYC is nothing but yield value of the card, and T is nothing but thickness of the card, right? This T. Yield value of FYC is the yield stress of the card. We have seen 0.8 times tensile strength, and Fs is the factor of safety, that's equal to 1.6. This is the value 1.6. And if you see here, this PA and MA, it is exactly same term. QU, QF, Fy T squared, Fy sin theta. QU, QF, Fy T squared, Fy sin theta into D, right? That means MA is nothing but
PA
whatever the
with distance
PA times,
or diameter.
yeah, PA times, yeah, this diameter of the brace, okay? Suppose if we increase the thickness, so if you see PA value is directly proportional to T squared. If you increase the card thickness, this is the card member, right?
I will increase the allowable also the capacity.
Yeah. This is the brace and this is the card member. Okay. So if you increase this thickness of the T, you can increase the allowable load on this brace. So it is directly proportional to thickness squared. And also FYC. FYC means yield value of this card member. If the card yield value, if I increase, allowable load also I can increase. And then these two parameters you will see, QU and QF. QU is the strength factor and QF is the card load factor. This card load factor is nothing but inside the card, some axial force can be there or bending moment can be there. So those values also impact this brace strength, allowable load on allowable axial capacity of the brace. Okay, because if it is already it's loaded, then if you apply some for example, if it is already loaded with tension card, then if you apply compression on this one, it cannot take more load because it will reduce the capacity. So the axial load, actual load on the card, that also influences the allowable load on this allowable capacity of this brace for the axial loads or bending moments also. That's why this QF is the card load factor. Okay, these things and all parametrical empirical values in the next slides we can see. So it is related to QF and QU. Both it is directionally proportional and indirectly proportional to FS, factor of safety, into sine theta. So suppose if my theta is 30, what would happen? Sine theta is 0.5, right? So that means my PA value increase. Suppose if I increase the theta to 90 degree, what would happen? Sine 90 is 1. That means PA value, it will come down. So as long as I increase the theta value, my PA value is coming down. Okay, right?
Yeah.
So PA
It's
and MA
biologic,
is, yeah, PA and MA is directionally proportional to P and MA also directly proportional, and also it is multiplied by diameter. So if I increase the brace dia, I can increase the moment value, right? If PA same PA, but diameter of brace is increasing, means my moment also, allowable moment on the brace also can increase. Okay. But there is a limit. Car diameter and brace diameter maximum we can go. That is diameter ratio beta we have seen, right? That's minimum is 0.2 and maximum is 1. So maximum we can go the diameter of the card only brace, because after that we cannot go also, right?
There is
Because
cannot
it
any
geometrically
joint.
not feasible. Yes.
Yeah.
Correct. And next one, if you see here, for joints with thickened cans, PA shall not exceed the capacity limitations as defined in 7.35. This we will see it in the next limit, like next slides, like what do you mean by joint thickened cans? Thickened cans means like we will have some higher thickness at this location. And for axially loaded brace with a classification that is a mixture of KYX joints, take a weighted average of PA based on the portion of each in the total load. That means like here if we have this the same joint also, this is Y joint, but this is T joint. So this will be like based on the axial load, it can 50% Y load, 50% T joint, 50% Y joint, 50% T joint. That kind of classification based on the load path and geometry we have. That also in the next slides you will come to know how to classify the joints based on the loads, and whether it's a T joint or X joint or K joint, Y joint, like that. We have different types of joints. Okay, that we will see it in the next slides. Okay. And you see, just now we have seen, right, strength factor QU.
Yeah.
QU, it varies with the joint and load type as given in the table 7.2. If you see here, table 7.2, it is there. Yeah, this is the QU. QU based on the whether it is a joint type and a load type, it will vary. If it is K joint, for axial tension, this parameter we have to use, axial tension or compression. This also has QG beta ratio. Beta and all we have seen. QG means that's a gap factor. Gap factor, it has some empirical value. So we need to define all these parameters. Then we can get for the K joint axial tension, this is the factor. For in-plane bending, these values are 5 plus 0.7 gamma beta. Gamma we know d by 2t, beta is diameter by diameter, brace dia by chord dia. So we can come to know all these factors like a QU values for a particular joint type and particular load. So we can calculate this and we can substitute this, we can come to know the PA value. PA is the allowable capacity of the brace. And you see here QU, where the working points of the members at a gap connection are separated by more than D/4 along the chord center line. That means this is, we have the chord member, this is the brace member. So this is a center line, this is the chord center line, this is another brace center line. If you see this point to this point, if this distance E eccentricity is greater than D/4, this D is nothing but this D diameter. If it goes more than that, this we need to model these two joints separately, and we need to analyze so that it can capture the bending additional secondary moments and all, because this force is coming here, right? This force also coming here. So this eccentricity we need to consider. That's what it's saying here in this one. Or where connection has simultaneously loaded branches members in more than one plane, the connection may be classified as a general or multiplanar connection. And this section also we will see, and it should be designed as described in section B.1. That's commentary we'll see. This QU factor is a big factor. You have to see like what is the joint classification and what is the load type. Based on the joint classification and the load type, we have so many empirical parameters. Based on that we can calculate. I will show you one Excel or MATCAD also how it was calculated. We have some basis to calculate these values. Okay. The next one is QF factor. QF factor is nothing but factor to account for presence of nominal loads in the card. This I just now explained, right? To account for the presence of nominal loads in the card, right? If I have the loads here, it will impact the PA value, right?
Okay. Yeah.
Yeah. So the how we are accounting this presence of load in the card is through usage of card load factor. So by calculating the card load factor and then putting this factor into the PA value, we can account the presence of nominal loads in the card. These also empirical, like C1, C2, C3, A. These are formulas only. This also we will see like how to calculate this one. And this FS is
Depending
nothing
on
but the factor
the
safety.
joint.
Yeah, correct. So to account for the presence of the load in the nominal loads in the card load factor is used. And card load factor, if you see here this parameter A, it is calculated based on factor of safety PC, PY, factor of safety MC, MP. This PC and MC is nothing but nominal loads, nominal axial load and bending moment in the card. This PC value and MC value. What is actually the load it is there in the card? PC value and MC value. And then this is the brace one. This is the card. In the card, whatever the axial load PC value and MC value that we need to include. And then PY is the yield capacity of the card. MP is the plastic moment capacity of the card. This card, whatever the yield capacity, that's the PY. And whatever is the card's plastic moment capacity, that is MP. MP means plastic. This Y means yield. So these two values also we have to calculate. Then once we substitute all these things, then we can come to know the parameter A. That parameter is the one here A. Then C1, C2, C3 is also depends on the joint type and loading type. K joints under brace axial loading, TY joints and brace axial loading, X joints under brace axial loading. It depends on the further classification beta less than 0.9 or less than or equal to 1. We have different C1, C2, C3 parameters. So once we substitute all these things, we will get the QF. So then we can account for the how the brace axial load, the card axial load, card bending moment, the nominal load, whatever it is there. By utilizing these values and we are calculating the factors, and then that factor is QF factor. That factor we need to put it on the PA, because PA is nothing but QU, QF, then T squared, then Fy also, it is the Fyc also there, then divided by factor of Ft into sine theta. This is what we have seen, right? Okay, then average of the card loads bending moment on either side of the brace intersections would be used in 7.3 and 7. This is the equation 7.4 and 7.3. And card axial load is positive in tension. Card resultant bending moment is positive when it produces compression on the joint footprint. So if it like this bending moment causes, this is the brace means, then if bending moment is like this in the card, that will produce top fiber on the joint footprint in the compression. So that moment is positive. And card axial load is positive in tension. That means like this is compression is negative. So suppose if the load is like in tension, then Py value is positive. The card thickness at the joint should be used in above calculations. Statistics are presented in, this is in the commentary, to permit both estimation of mean strength and performance of reliability analysis. And this is okay, we will see the commentary later stage. But at least now you know how to, what do you mean, how we are calculating PA, MA value, what do you mean by PA and what do you mean by MA. All these things, at least you'll be having some idea about it, right? And how it depends on the, what are the parameters are there like that. And this is the what like last time we have seen like joint with thickened cans. Okay, thickened cans, PA is R plus 1 minus R Tn by Tc and PA C squared. This PA value now what we calculated based on QA, QC, that value. And after that, see if you have thickened joints like this, suppose if here we have higher thick and after that nominal thick, this is the nominal thick, nominal card, and this is the card can, TC. So card thickness is more. In that case, we need to calculate this LC, card length, how big it is the card length. For example, brace 1. If we have only one brace, this brace only we have D1 means what will be the value here A and another A it will be here and this D1. So 2A plus D1, that's the card length. That means like this we have the card and we have only one brace. This is the D1 and here we have the thickened can and here we have the nominal value. That means like it will be like this. This is the can, this is the nominal value, nominal thickness, and here we have the brace. So from here to here, it's a value. This is the D1 value. Then this is also A. That's what this is card length. So card length means from here to here is the card length, LC value. And then 2B plus D2 sine theta is for this D2 because it's in inclined. So theta means from here to here it will be the sine theta. Then here 1B and another 1B it will be coming. So B value, and third one is 2C plus D3. Here if it is C, another C here this side and D3. So this is basically calculating the geometrical card length. Okay, after calculating that card length, then we can substitute here in this formula, then we can get the PA value, updated PA value for the thickened can members. PA, like your previous equation, we are calculating based on the card can geometric material properties, including QF calculated with respect to the card can. Tn is the nominal card thickness, Tc is the card thickness. Tc is higher always, nominal will be less. So R value here, this some R value is there, right? How to calculate that R? That R is based on the length of card divided by 2.5 times diameter. So it depends on the length of the card member as well as diameter of the card member. So how to calculate the length of the card member? That's what we have seen here. So once we know these things, then we can substitute and we can get the R value. Once we know R value, we can calculate the PA value for the thickened can members. So LC is the effective card length based on this below that figure we have seen, right? In no case R shall be taken greater than unity. In no case it will go more than 1. So this also depends on, like, this formula LC by 2.5D also depends on the beta value. If beta is less, we can go with this straight away. If beta is more, then once again 4 beta minus 3 divided by LC into 1.5 times D. That way we have to calculate the R. Alternatively, the approximate closed string analysis may be employed, including plastic analysis, using appropriate safety factors, using an effective card length up to 1.25 either side of the line of action of the brace loads at the card face, but not more than the actual distance to the end of the can. It means like if you are doing alternative method, we have the brace like this, means from this end and from center, right? From center to card length, it's 1.25, 1.25. That means total it will come 2.5 times D. That's the value they are using it here. So normally at least minimum we need to have this 2.5 times the diameter of the card member as a can. We need to consider whenever you might have seen, like, we use some hatch material. You have seen, right, in the drawing, you might have seen the card member. So this length at least it should come 2.5 times the diameter of the card. That's what it's saying here. And any reinforcement with these diamonds and diaphragms, rings, gussets, stiffening effect of the plane, that and all we need to consider it, and maybe consider in the analysis, although it is effectiveness decreases the distance from the footprint. Suppose if you are adding some like a ring here, even though if it is away from the footprint, it will have some minor impact, but if it is too much away, it will not add up any strength to the card member. Then here we have to see strength check. This is simply the interaction ratio, like our AIC and all, we used to have interaction ratio, right? Actual axial plus bending, that will axial stress, the utilization ratio, and moment in plane and moment of out of plane. If we calculate the interaction ratio, it should be less than 1. Then we can say the joint is passing. Okay, then if you see here, design loads and joint flexibility, adequacy of the joint may be determined on the basis of nominal loads in both brace and card. Yeah, so this is the card member, this is the brace member. Whatever the loads are coming, nominal loads, based on the loads, we can calculate whether the joint is having sufficient capacity or not. That's how the adequacy of the joint we can determine. Reductions in secondary deflex-induced bending moments or inelastic relaxation through the use of joint elastic stiffness may be considered, and for ultimate strength analysis of the platform, information concerning the force deformation characteristics of the joints may be placed. It means nothing but when we are using some ultimate analysis, like some resource strength analysis and all, we need to consider this joint flexibility. Why we are telling, right? If we have the card member like this and brace like this, it's not that it is always it's rigid. It can also rotate because of the moment. What will happen locally, it can rotate. So this joint is having some flexibility. It's not that it's completely rigid joint. Even we have, when we have like moment connection and all, we used to say this is a rigid connection. It's not always rigid. It will be having some flexibility. That flexibility we can utilize. That's what they are saying in this code. And the calculations are dependent on the joint type, configuration, geometry, material properties, load case, and in certain cases the hydrostatic pressure effects also. This we will see for more information in commentary. Hydrostatic pressure effects also, it impacts the joint can, but usually it won't have much impact because it's a very thick members. It will come only for the members, jacket leg member, sleeve member, where the thickness is less. That location combined with axial load plus hydrostatic pressure, it will reduce its load carrying capacity of the members. Let us see here this minimum capacity. Yeah, I think sometimes back we have told you like a load UC and strength UC. There are two kind of values. We take it from the SACS output, software output, and we will compare. Both should be less than 1.0. In both cases, if it is less than 1.0, we can say that the joint has passed and joint is safe to whatever we size, joint is safe to carry the load. So this strength UC, that's the one what we are talking about here in the minimum capacity. So here If you see here, cards at the ends of primary tension and compression braces, in addition to developing the strength required by the design loads, shall also have the minimum capacity of at least 50% of the effective strength of each incoming brace for each design load condition in place, load or lifting, launch, accidental. Do you understand what do you mean by these sentences? What does it say? It means that suppose my can is there, my brace is there. Actually, some load will be coming, 10 only it will be coming, but my brace can take the capacity of 20, say 30 ton. 30 ton the brace can carry the load, but due to some reason like my load is coming only 10 ton only, effectively from equipments and other things it's only 10 ton only it's coming. But doesn't mean that we have to design the joint with only for 10 ton. We need to design at least 50% of the capacity of this brace. That means I need to design it for 15 metric ton.
Yeah.
That's what called the minimum capacity requirements. Okay.
But what if it is less than 50%? So is it okay or just for as an economic issue?
Sorry?
If it's less than 50%.
Yeah, if it is not designed for 50%, that's what you mean.
Yeah.
Yeah, it
Is it
means
just
that
for the economy to just reduce the
I
cost
got
only?
it. I got it. Yeah, no, we can't say that the cost is one hand, the safety is another hand. Here, there are so many uncertainties are there, and when we design it, this joint, I don't want the joint to fail first, the member to fail first, right? Here, safety we cannot compromise with respect to economy. If we compromise safety with respect to economy, then we have to bear more cost it will come. So safety is much important than
Economy, yeah.
economy. So we need to consider this 50% strength requirement. Suppose if 50% strength requirement, we can waive this member, brace member, or this joint can is very minor one. If even if it fails, my entire structure does not collapse. Like not a main joint, it's a miscellaneous joint, some non-important joint. That locations definitely we are not going to check with this 50% capacity. Only load use we will check it. All those miscellaneous joints, secondary joints, walkway kind of thing, or some attachment kind of thing, that's even if it collapses it doesn't matter. Like, so those joints we will not check this strength UC. What I mean that we are not checking the strength UC for all joints. Only non-critical joints we will not check the strength UC. Critical joints we are supposed to check. Critical joints, how do we define? Means that's important for the safety of the platform. It should not collapse for the entire structure. So it should have some sufficient resource strength, and that's why we check those critical joints for this minimum strength check, and non-critical joints we can exclude. That also it is set in this specification. It is already clearly defined in the specification. Okay. So earthquake loading. For earthquake loading on L2 platforms not analyzed for robustness, the card capacity should be at least 100% of the brace effective strength. So for seismic analysis, we will take this instead of 50%, we will take the 100% of this joint and then check the card member, because we don't want to have some complete collapse of the platform for this seismic analysis. But that time what we will do, we will be increasing this joint A mode allowable modification with the 1.7 70% increase in the allowable stress instead of 1.33 for the extreme cases. So, but we will be carrying the 100% of the brace load to check. This is what code requirement. Okay. And effective strength, everywhere we are talking about effective strength, 50% of the effective strength of the each incoming brace. We are saying effective strength of each incoming brace. So what do you mean by effective strength? How do we calculate? So that's what it's given here. Like effective strength is nothing but the effective strength of the brace is defined as the yield load of the brace for braces loaded primarily in tension, and ultimate buckling load of the brace for the braces loaded primarily in compression. If the brace is loaded primarily in compression, then we need to take the buckling load. If the brace is primarily loaded in tension, we need to take the yield load. So that yield load is the effective strength. Here buckling load is the effective strength. It depends on whether the brace is subjected to primarily in tension or primarily in compression. And inelasticity should be considered in the calculation of ultimate buckling load. So we need to consider the inelasticity. Inelasticity means like sometimes it can go little plastic also, right? So that should be considered in the ultimate buckling load. In buckling load, we can say that members, extreme fibers can go to the yield value and all. The effective strength calculations should be based on the nominal material and geometrical properties of the brace, not of the brace stub. One thing I want to tell, this is the card member. We have the brace member like this. Sometimes what will happen, we will be having at the end of the brace, we will have somewhat higher thick brace, and then other locations we will have lower thick brace. So this is the nominal tubular thickness, and this is the stub member. So when you are taking the stub member, means it will have higher thickness. If higher thickness means it will have the higher yield load and also higher buckling load. So we should not take that stub strength to check the joint can for this effective strength. We need to take the nominal strength of the brace. That means the reduced thickness of the member we need to consider for checking the joint can. Okay, that we can check in the sacks also. And for the purpose of this requirement, the card capacity should be determined equation 7.1 with a factor equal to 1, and strength factor, card factor shall be consistent with the design of the loading condition being considered. So what does it say? The factor of safety we have seen 1.6, right, in our previous slides. But when we are calculating this minimum strength capacity, we can take the factor of safety as 1 instead of 1.6. So that it is given in defined in this code. Then next one is weld in connections. Welds in connections at the ends of the tubular member should be in accordance with these specifications. There is some welding specification that we will see it, and should not be less than the required to develop the capacity equal to the lesser of strength of the branch member based on yield, strength of the card, basic capacity equations where applicable. It means like when we are checking the weld should pass. We should not put lower grade weld, so that weld becomes problem. Okay, so weld also it should have some sufficient capacity that should be more than this kind of strength of the brace members and all. It should develop, right? It should not be less than these two, so that a joint can suitably that weld can pass the load. Okay. Next one, joint classification. This is what I was telling sometimes ago, like some joint, if we have the brace like this is a K joint or X joint or T joint, some combination Y joint and T joint. All these joint classifications are there. So how do we classify the joints? And that guideline is there. That guideline only now we are going to talk about it. Okay. See, joint classification is a process whereby axial load is given and the brace is subdivided into K, Y, X components of the loading corresponding to the 3 joint types for which the capacity equations exist. Now, what does it say? It says that based on the axial load in the brace, whatever the loads are coming in the brace, I will show you here. Whatever the loads coming in the brace, based on this load, we can define this whether it's a K joint or a T joint or Y joint like that. That's what it says here. And for each joint, it's a separate equations exist, because we have seen, right, that QU factor and all. K joint means different QU factor, TY joint means different QU factor, X joint means different QU factor. So based on this joint type, and we have different capacity equations. Such subdivision normally considers all the members in one plane at a joint. For the purpose of this provision, brace planes within the 15 degree of each other may be considered being in a common plane. Suppose if you see in the tubular like this one tubular is coming here and another tubular is coming here, some 15 degree away from this plane, that also we will consider as a one single plane, common plane. all these members we need to consider. Suppose if some brace is coming like this, that is in different plane, that is more than 15 degree, that will be the separate plane, that we need to analyze separately. That's what it's saying here. Each brace in plane can have a unique classification that could vary with load condition. The classification can be mixed between the above three joint types, KY, KXY, and T also is there. Once breakdown into axial components is established, breakdown into axial components means based on the loads, whatever the loads it's coming, based on that load, if we establish like axial breakdown of this axial components, the capacity of the joint can be estimated using that procedures on point, like whatever we have seen earlier. Figure 7.1 provides some simple explanation of joint classification. For brace considers K joint classification. Axial load in the brace would be balanced to within the 10% by loads in other braces in the same plane on the same side of the joint. For Y classification, the axial load in the brace is reacted as the beam shear in the card. For X classification, axial load in the brace is transferred through the card opposite of braces. 1 minute, let us see here. You see here, K joint,
Yes.
here 1000 kN, 1400 kN. So that means it both are almost equal loads. So it is considered as a K joint. And here this joint is no load, but here it is 1400 is coming. That means it will look like a Y joint because this doesn't have any load. Even though this both are same configuration. You see the brace is like this, brace is like this, but it does not have any axial load. So this load we can say it's a Y joint with the shear also. But in case if we have the shear and we have some load here and some load here, that means this is K joint, this is Y joint. So 50% K, 50% Y, like that it will come. And if you see this one, here we have some load and here same load is going out and here nothing is there. So it will be a K joint. But suppose if we have some load here, 500, 1400 to 2000, this joint is K joint, this also K, this also K. Suppose if you don't have any joint loads here and we have the load here, means it becomes like X joint. Even though it looks like this, it's X joint. Here if you see here, this is K joint because we have loads on different plane. Here it's like a 50% K, 50% X. Like that we have, the concept is that based on the loading, we are classifying the joints. You see figures on case H, we will see case H. Case H is where, yeah, this one. What is the load? 50, 500, 500, 1400, 50% K, 50% X. It says here, figure 7 is a good example of the loading and classification hierarchy that should be adopted in the classification joints. A replacement of brace load by a combination of tension compression load to give the same net load is not permitted. Okay, actually, if you see this net load here, suppose it's 1000, here 400 means net it will be 400. That means only these two only loading is there, here no load. Like that, we should not have a net load. It will become Y joint. Actually, it should be considered as X joint only. It should not be considered as a Y joint. Net load we should not consider. That's what they mean. Special considerations should be considered to establish the proper gap if portion of the load is related to K joint behavior. See here one more thing also. Here we have seen if this is gap, here you see the gap and here also gap is there. So this gap also important while we define the K joint. That is okay. Detailing practice. This is very important thing. Even though we can design our joint like very like a proper size, proper thickness, but if we don't detail it properly, it will not solve the purpose. Joint detailing is an essential element of a joint design. So whenever we are saying we are designing the joint, it means you are supposed to detail it also. So joint detailing is the essential part of joint design. Essential element. For unreinforced joints, the recommended detailing nomenclature dimensions shown in this figure. This practice indicates that if an increased card wall thickness, if you are increasing the card wall thickness, it should extend past the outside of the edge incoming brace by a minimum 1/4 of the card member or 300. If you see here, this is what I want to tell you. See, if you are increasing the card thickness, it should go at least 300 mm from this joint to here. 300 mm it should go out. Okay, Majid?
Yeah, I'm with you.
Okay. So it should go when you are increasing the increased card member is there, it should go from here to here 300 mm. It should go. That's what it's saying here. And D before or 300, whichever is greater. Even greater lengths of the increased wall thickness vessel steel may be needed to avoid downgrading of the joint capacity in accordance with 7.35. Suppose if you are even if you are keeping 305, sometimes we cannot have the full capacity. It should go little extra. Otherwise, we need to degrade the joint capacity. That's what it's saying here. And if an increased wall thickness of brace or special steel is required, it should extend minimum one brace diameter 600 mm, whichever is greater. That is nothing but here you see, this is the brace. So this brace, we are having higher thickness. If we are having higher thickness, if we need higher thickness for the joint design purpose, it should go minimum 600 mm. We should not keep only 300 mm. So it should have some like a more length. The same way here also it should have 300, right? The same way if we have the brace, it should have 600 mm more. Even if we have seen this kind of overlap, this joint overlap, this should come minimum 150 mm overlap or d by 2 4. And whenever there is a change in the thickness transition, it should have 1 in 4 thickness. 1 in 4 that transition it should come everywhere, wherever it have 1 in 4 transition should come. And here if you see like a gap between these members, it should be minimum 50 mm. And when we have, this is the longitudinal seam I told, right? Seam. This seam should come at least minimum 300 mm or 12 inch from this brace footprint. It should be separated from here. Sometimes inside also we can keep it, but that time also it should be separated from the wall footprint. Okay. This is what it's giving in this detailing one. Neither sighted card can nor braced of dimensions include the length of over 1:4 thickness taper occurs. It means, see, whenever we are saying this is the stub thickness, the transition should come after that. Minimum that 600 is the right, minimum 600 is the higher thick. After that only transition should come. Here also minimum 600, 300 means higher thickness should come 300. After that only transition should go. Okay. Here also the same way, like wherever higher thickness we need, we have to put higher thickness. That 600 we are saying, right? That 600 does not include this transition. That's what they mean here. In situations where fatigue considerations can be important, tapering on the inside may have an undesirable consequence of fatigue cracking originating on the inside surface and be difficult to inspect. See, whenever we have this kind of transition, 1 in 4 transition. If it is inside, what they are saying that in the fatigue problems, it is difficult, like maybe some crack is happening inside, it's difficult to inspect. So when it's preferable to keep the transition outside. Tapering of the inside may have undesirable consequence for fatigue cracking. The minimum nominal gap between the adjacent braces, whether in plane or out of plane, is 50 mm. And care should be taken to ensure that overlap of welds at the toes of the joint is avoided. So that means like this kind of overlapping, we try to avoid that one, because overlapping it's not preferably used. And even if overlapping occurs, the amount of overlap should preferably at least d by 4, or d is the diameter of the brace, or 150 mm, whichever is greater. So we need to see what is the diameter of the brace divided by 4. If diameter of the bridge is 1 meter, 1 divided by 4 is 250. So the it should not be minimum 150 mm, it should be 250 mm it will come. So whichever is greater we have to see for this overlap. This dimension is measured along the axis of the through member. Where overlapping of brace is necessary or preferred, that different nominal thickness by more than 10% of the brace, which higher wall thickness should be the through brace and fully welded to the card. It seems like where overlapping of the brace is necessary or preferred, that differ in nominal thickness by more than 10%. Suppose one card member is higher thick, another card member is lower thick, the higher card thick only should go inside. That's what they are telling here. Further, where substantial overlap occurs, largest diameter brace should be specified as through member. The brace member may require an end stub to ensure the thickness at least equal to that of overlapping brace. That's okay, that we will see it. Yeah, this one, longitudinal seam welds and girth welds should be located to minimize or eliminate their impact on the joint performance. You see here, this is the one girth weld, and you see here this one, the longitudinal seam weld. So Majid, if you see here, this gut weld, this is the gut weld, this is the longitudinal seam weld in the brace. So we are seeing this longitudinal seam weld gut weld should be located to minimize or eliminate the impact on the joint performance, because wherever we have the weld, it will have some impact on the joint performance. So if we place those weld at a particular location, we can avoid those impacts in the performance of the joint weld. So the longitudinal seam of the weld of the card should be separated from incoming braces by at least 300 mm. See figure 7.3. This is what I told here. See here, from here, this point to this, minimum 300 should come. Longitudinal seam of the card member should be, longitudinal seam weld of the card should be separated from incoming braces. This is the card member. This is the incoming brace member. From this brace, it should be separated at least 300 mm. Okay. So that if you place like this, it will not have any impact. It will have impact with a minimum impact on the joint performance. Okay. The longitudinal seam of the weld of the brace would be located near the crown heel of the joint. This is the one we have seen, right? This is the saddle, this is the crown, this is the crown, this is the heel, this is the toe. So on the heel side, we need to put this longitudinal seam. Okay, that's what they are meaning it here. So suppose if we have this card, and this is the my brace, and this is my crown toe, and this is the crown heel, and this is the saddle. So I need to place this longitudinal seam near to the heel. This is the heel. Okay. And the longer cord cans may require girth weld. If this can member, see here, from here to here, this is the can member. This much length we may not get also. So we may need to add some additional girth weld. Two pieces we need to weld together to produce that much big can length. Okay. So in that case, longer cords can require additional girth weld. This weld should be positioned at lightly loaded brace intersection between saddle and crown location. So lightly loaded, see this is small brace. This brace, see this is the can member. I have this small brace. So what does it say? This is the small brace. This is the lightly loaded brace, not heavily loaded brace. That location only we need to keep the girth weld. And this also between this card and saddle. If you see here, this would be the saddle and this is the card. Sorry, not the card. This is the crown. Crown. This is the saddle. Between these two, we need to place this girth weld. That's what it is saying here. Okay. And this we have already seen. This also we have seen it. Overlapping joints also we have seen it. Grouted joints, if you see here, two varieties of grouted joints are commonly occur. First relates to the fully grouted card. If you see here, this may be card member, this is the brace member. What is they are saying that this fully grouted, that one type is there. Another one is double skin type. That means like we have one jacket leg and then pile, then we have the brace. Then in this, in between these annulus, it's getting filled. Grout is that. That is called a double skin type. So where grout is placed in the annulus between the card member and internal member, that is double skin type. In both cases, grout is unreinforced. We don't have any reinforcement in the grout. As far as the joint behavior is concerned, benefits of shear keys that present, it should not be permitted. For grouted joints that are otherwise simple configuration, the simple joint provisions, whatever we have seen earlier, should be applied with below modifications and limitations. You see here the QU factor. QU factor is the strength factor that is getting changed, and that should be modified while calculating that PA value and MA value. Okay, that's what it's saying. The double skin type, we have the effective thickness, the T and T. T is the inner member wall thickness, and this is the card wall thickness. So effective thickness will be square root of card thickness plus pile thickness. That's how we need to calculate the effective wall thickness. That should be used in the PA value, or calculating the PA value, because failure may occur in the card by card ovalization also. The ovalization capacity can be estimated by substituting the following thickness into the simple joint equations. So we need to consider the effective thickness, so used in place of the T and including the gamma term also. The QF calculation for both filling router double skinned should be based on the T. It is presumed that calculation of QF has already accounted the load sharing between the card and inner member. That's okay, that's not a problem. Minimum capacity we have seen already in the 50% capacity. Internal ring stiffened joints. Primary joints along the launch truss and steel jackets are often strengthened by internal ring stiffening. Internal stiffening is also used in some structures to address fatigue requirements to avoid very thick card cans. Outline salient features for several common approaches to design internal ring stiffened joints. This I will explain later. Like sometimes what we will do, we will not increase the card thickness to a heavy thick member. We may go with the internal ring stiffness. So that internal ring stiffness, how to design, some features are explained in the commentary that we will see it later. Cast joints and all, normally we are not using it our offshore structures. And other circular joint types. Joints covered in this one may be designed on the basis of approximate experimental numerical in-service evidence. Whatever this Q factor, QA factor, all these are experimental factors only. So we are using those values. Let us see, like we can go with some finite element analysis also. Damaged joints. Joints in existing installation could be damaged as a result of fatigue, loading, corrosion, overload, or environmental accidental. In such cases, reduced joint capacity can be estimated either by simple models, reduced area, reduced section models approach, or calibrated FE models, experimental evidence. Suppose if already joints are corroded or damaged or some reason, we can consider its reduced area or reduced section models, so that we can reduce its capacity and we can estimate reliably their joint capacity. Non-circular joints, like all these rings where we have the bearing type connections, that is basically we are going with I column, all these things by our AAC method only. That is okay. See, we have some API check for using this is the math card sheet. It will have, like, we need to give this parameter tau. We know tau ratio, thickness by thickness, thickness of brace by thickness of card. Beta is diameter of brace by diameter of card. Gamma is diameter of card by 2 times thickness of card. We can put all this, we can define it, and we can come to know what is the UC ratio, right? So from this, all this you see the A factor parameter A we have seen, right? QF factor, Q in plane, out of plane factor, all these values and all we can put it in the Excel sheet also. We can do it.